This is SpaceTime Series 21, Episode 20. Coming up on SpaceTime, astronomers detect ancient signals from the first stars in the universe, a new kind of star hypothesized, and Juno's newest close encounter with the king of planets. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have for the first time ever detected ancient signals from the first stars in the universe. The discovery, reported in the journal Nature, places the first stars at just 180 million years after the Big Bang, far earlier than previously thought. Cosmological models of the early universe indicate it was created through a violent explosion some 13.82 billion years ago. However, it wasn't until some 378,000 years later, as the universe expanded, that this primordial soup of photons, electrons and quarks had cooled enough for protons, neutrons and electrons to come together, eventually forming the first neutral hydrogen and later helium atoms. Still, the universe at this stage was a hot white opaque fog of plasma. But as these first atoms formed, photons were able to decouple from matter and move more freely through the cosmos, allowing the universe to become transparent. We can see this epoch of recombination today in all directions across the sky as the cosmic microwave background radiation, which permeates the universe, the faint afterglow of the Big Bang, now cooled to just 2.73 degrees above absolute zero. Slight temperature variations in the cosmic microwave background radiation are caused by density fluctuations at the time, which were the first seeds of galaxies and galaxy clusters. And these overdensities would eventually collapse under their own gravity, forming the first stars and galaxies. These first stars, which astronomers call population 3 stars, were made out of the pure hydrogen and helium created in the Big Bang, allowing them to all be massive hot blue stars, dozens to hundreds of times bigger than the Sun. Being so massive and hot, these first stars burnt through their fuel supplies incredibly quickly, living fast and dying young. It was thought that these first stars formed about 400 million years after the Big Bang, ending what was known as the Cosmic Dark Ages and sparking the epoch of reionization, when the ultraviolet radiation from these first stars began turning the neutral hydrogen back into an ionized plasma, starting the process of giving the universe the appearance it has today. However, these new detections suggest the first stars were already shining just 180 million years after the Big Bang, far earlier than anyone expected. Astronomers from Arizona State University, the Massachusetts Institute of Technology MIT, and the University of Colorado at Boulder discovered the signal in an experiment to detect the global epoch of reionization signature, known as the EDGES project, using a radio antenna looking like a kitchen table and not much bigger than a refrigerator set up in outback Western Australia. The study's lead author, Judd Bowman from the University of Arizona, says finding the signal has opened up a new window on the early universe. Because optical telescopes can't see far enough back to directly image these first ancient stars, astronomers have instead been hunting for indirect evidence, such as a telltale change in the cosmic microwave background radiation. A small dip in intensity, for example, should be apparent in cosmic microwave background radiation signals. The problem is Earth's crowded radio wave environment has always hampered such searches. That's because these dips occur at wavelengths between 65 and 95 MHz, thereby overlapping some of the most widely used frequencies on the FM radio dial. As well as that, there are booming radio waves emanating naturally from throughout our Milky Way galaxy. Peter Krasinski from the National Science Foundation, which funded the project, says all this makes detection of the signal a massive technical challenge. Other sources of noise can be up to 10,000 times brighter than the signal the scientists are looking for. He says it's a bit like being in the middle of a hurricane and trying to hear the flap of a hummingbird's wing. But despite the obstacles, astronomers were confident that finding such a signal would be possible. That's thanks to previous research indicating that these first stars would have released tremendous amounts of ultraviolet radiation. That light interacted with free-floating hydrogen atoms, which began absorbing the surrounding cosmic microwave background radiation photons. Co-author Alan Rogers from MIT's Haystack Observatory says this allows you to see the hydrogen gas in silhouette at specific frequencies, providing the first real signal that stars are starting to form and starting to affect the interstellar medium around them. The EDGES team reported seeing a clear signal in the radio wave data, detecting a distinct fall in cosmic microwave background intensity when that process began. As the stellar fusion continued, it's resulted in ultraviolet radiation beginning to rip apart the free-floating hydrogen atoms, stripping away their electrons through ionization. When these early stars died, black holes, supernovae and other objects they left behind continued the ionizing process, heating the remaining free hydrogen with X-rays and eventually extinguishing the signal. And the EDGES data reveals that milestone occurred roughly 250 million years after the Big Bang. EDGES began more than a decade ago when Berman and Rogers first proposed building a unique antenna with a specialized receiver, a system that could detect clean signals across the target radio band. Through a series of National Science Foundation grants beginning in 2009, the researchers built the instrument, honed calibration methods, and developed statistical techniques for refining signal data. The authors set up the EDGES antenna in the desert to eliminate as much radio noise as possible, selecting an isolated site at the CSIRO's Murchison Radio Astronomy Observatory in the Western Australian outback. Once the signal emerged in their data, the astronomers initiated a years-long process to check and recheck their findings against any known causes of instrumental errors and to rule out potential sources of radio interference. In all, EDGES applied dozens of verification tests in order to ensure that the signal truly was from space. However, while confirming the signal, the EDGES data has also raised some new questions. That's because the signal's about twice as intense as what the models had predicted. The authors suggest this means that either the fog of hydrogen gas so soon after the Big Bang was colder than expected, or that background radiation levels were significantly hotter than the photons of the cosmic microwave background. Teams suggest one possibility is that dark matter interactions could explain the effect. Berman says if confirmed, this will provide the first glimpse of physics beyond the standard model, hinting at something new and fundamental about mysterious dark matter, which makes up some 85% of all the matter in the universe. The idea that these signals implicate dark matter is explored more closely in a second paper also published in Nature. The research by Professor Renan Barkana from Tel Aviv University suggests that the signal is proof of interactions between normal matter and dark matter in the early universe. Barkana says the discovery offers the first direct proof that dark matter exists and that it's composed of low-mass particles. And that's important because dark matter is key to unlocking the mystery of what the universe is made of. While scientists know quite a bit about the elements that make up the Earth, the Sun and other stars, most of the matter in the universe is this invisible dark matter. Right now we know about dark matter only because its existence is inferred by its strong gravitational effect on normal matter. The problem is we have absolutely no idea what this substance is made of, hence dark matter remains one of the greatest mysteries in physics. Berman and colleagues reported their detection of the radio signal at a frequency of 78 MHz. Barkana says while the width of the observed profile is largely consistent with expectations, they also found a larger amplitude than predicted. That corresponds to deeper absorption, and that indicates the primordial gas was colder than expected because, according to Barkana, the gas would have cooled through an interaction of hydrogen with cold dark matter. Barkana hypothesizes that the surprising signal indicates the presence of two actors. Firstly, the first stars, and secondly, dark matter. The first stars in the universe turned on the radio signal while the dark matter collided with ordinary matter to cool it down. Extra cold material naturally explains the strong radio signal. Problem is, physicists always expected that dark matter particles would be heavy, but this discovery indicates that they'd be low-mass particles. Based on the radio signal, Barkana argues that the dark matter particle is probably no heavier than several proton masses. If correct, that's an important insight which has the potential to reorient the search for dark matter. Once stars formed in the early universe, their light was predicted to have penetrated the primordial hydrogen gas, altering its internal structure. This would cause hydrogen gas to absorb photons in the cosmic microwave background in the 21 centimetre wavelength band, imprinting a signature in the radio spectrum which should be observable today at radio frequencies below 200 MHz. And the observation totally matches this prediction, except that is for the unexpected depth of the absorption. But Canner predicts that the dark matter produced a very specific pattern of radio waves that can be detected with a large array of radio antennas. One such array will be the SKA, or Square Kilometre Array, the world's largest radio telescope, now under construction in Australia and southern Africa. But Canner says such an observation with the SKA should confirm that the first stars did indeed reveal dark matter. The CSIRO's Professor Ron Eckers says the fact that the signal is twice the most optimistically predicted amplitude was not expected, and certainly not predicted.
We have a thing called the Big Bang, the radiation that came from the beginning of the universe. So that radiation then has to travel from essentially the beginning of time through a very early stage in the universe where stars were first forming. And in that period, things change a little bit, and the radiation from the Big Bang gets distorted. So they're not actually observing radiation from the first stars that are forming. They're watching the way in which something, which may be the first stars that formed, distorted the radio waves as they went past.
How do they determine the age of what they're seeing in their signals?
Well, what you're looking for is the very simplest kind of matter in the universe is hydrogen. One proton, one electron. It's the very simplest form of matter. And that is the first atom that starts forming in the universe. The universe started out in what was called this hot Big Bang. All the protons, electrons and photons were all separate. Then it starts to recombine, and you have to have these atoms before you can start forming regions where there are stars. Now, as soon as you have a proton and an electron combined into this hydrogen atom, the energy levels are slightly different depending whether the proton and the electron are spinning the same direction or opposite direction. So that difference in energy level is what absorbs and re-emits the radio waves. There's a very precise radio frequency at which that happens, and it's 21 centimeters. But this happened near the beginning of the universe, and the universe has expanded by about a factor of 20 since that time. So this 21 centimeter radiation is now 4 meters long, and that's the signal they look for. They look for a distortion. They didn't know exactly which frequency it would be, but where they see a bump, that tells you how old the universe was when the radiation was distorted.
And that ties in with population 3 stars.
One of the predictions about when you will see this signal relates to what's called ultraviolet light, which gets emitted from the first population 3 stars. And that ultraviolet light changes the hydrogen atom just a little bit so that you can start to see this signature. However, that's only one interpretation. Something happened at this time, most likely population 3 stars, and that's what all the stories you're hearing say. But we don't actually know. We certainly don't see the stars themselves. Maybe it was X-ray emission from early black holes. Whatever it is, very interesting. And it's also telling us that the gas was starting to collapse and form things at that stage. So I'm just being slightly wary here that it is an interpretation that it's pop 3 stars. We don't see them directly.
It's a time when the reionization of the universe is getting underway, and that is being caused by pop 3 stars, which is, I guess, why they're looking at it that way. Would that be right?
Well, the stars have to form at some stage, so this is quite a good theory. I'm just being a little cautious as a scientist, and I like to compare things that we are sure about and separate them from the ones which we are a bit less sure about. We know, for example, that there's going to be radio emission at this 21 centimeter redshifted. That's very basic physics. Nobody would have any question about that. Whether it was the radiation from these stars, whether something else happened when the first stars were forming, that's a little bit speculative. We know there couldn't have been any stars much earlier before this, and later there are stars, and as you said, they then start reionizing and heating the hydrogen. When you read most articles about people trying to look for signals from the early universe, it's that reheating phase that most people are going after. But these guys have picked a signal up which is perhaps it's a bit stronger than expected. So, and it's come from this slightly earlier phase where things are collapsing for the first time.
It's not just a bit stronger than expected, it's almost twice as strong as what they were originally expecting, and that's raised...
Can I correct you there?
Sure.
In the paper they say almost twice as strong, and I think that's because they don't want to... if you make extraordinary claims, you need extraordinary evidence. It's actually about 4 times what most people predicted. Their factor of 2 was based on the most optimistic prediction they could find in the literature. But if you take typical predictions, it's a factor of about 4. And that's very, very significant.
Yeah.
And that's why other things are being speculated, like
dark
you
matter.
need something else. You can't do that with the standard model of stars changing the state of the hydrogen. So one of what will be many possible explanations is that the dark matter is doing it. I'm now being a little bit cynical about our theorist friends, but when you have dark matter and you really don't have any idea what it is, you have a lot of flexibility to make a theory.
Yeah.
The way science works is, here's an observation to be explained. And that's where we really start making advances, because some of these theories will turn out to work, some won't, and we'll then start to understand more about this early phase in the universe.
That's the CSIRO's Professor Ron Eckers. And this is Space Time. I'm Stuart Gary. Okay, let's take a break from the show for a word from our sponsors, the Great Courses Plus. Like you, there are so many things out there in the world that really fascinate me, things I want to learn more about. And that's where the Great Courses Plus comes in, now available in Australia and the UK, as well as the United States and Canada. With the Great Courses Plus, you have unlimited access to thousands of video and audio lectures, learning from some of the best in their respective fields. And you can learn just about anything of interest. For me, obviously, it's astronomy and physics, but you can also learn history, psychology, or even how to take better photos. The Great Courses Plus gives you lifelong learning, with the very best guiding you every step of the way. Now, one of the courses I've been checking out over the past couple of weeks, and one which I can recommend to you, is Understanding the Universe, an Introduction to Astronomy. As I mentioned last week, the course is presented by Alex Filippenko from the University of California, Berkeley, and it teaches you the basics of astronomy and a lot more. Now, the way the professor goes through the subject matter, it's really easy to understand, but if there is something you're not quite sure of, it's easy. Just hit the pause button, go back, and review the material. One of the reasons I love the Great Course is because I do a lot of travelling and I can take it with me wherever I go. So if I'm in the car, if I'm on a train, if I'm flying somewhere, I just pop in the earbuds and listen to the Great Courses wherever I am. It's my ideal way to productively spend my time. And to help you get started with the Great Courses Plus, we have a special offer. For a limited time, you'll receive a special 1-month free open unlimited access to all of the Great Courses lectures. But to get it, you'll need to use our special URL, thegreatcoursesplus.com/space. You can start your free 1-month trial today. Just sign up at thegreatcoursesplus.com/space. That's thegreatcoursesplus.com/space. And of course, I'll put the link in our show notes. And now, it's back to the show. Scientists are speculating about a new type of hypothetical stellar remnant born out of the death of a star. If they exist, these so-called semi-classical relativistic stars should look like stellar mass black holes, but without the black hole's event horizon to provide a point of no return for energy, matter and time. The research, reported in the journal Physical Review Letters, suggests a novel mathematical model combining general relativity with the repulsive effect of quantum vacuum polarization. The idea that empty space really isn't empty, but filled with virtual quantum particle pairs of matter and antimatter popping into and out of existence. These short-lived virtual particles were thought to have no measurable impact on any process. However, the evaporation of black holes through Hawking radiation and the Casimir effect acting on two closely positioned uncharged conductive plates in a vacuum show that these quantum bubbles, for want of a better term, do impact our universe in a very real way. A star is usually in a state of hydrostatic equilibrium between the force of gravity pulling it inwards towards the centre and the pressure caused by nuclear fusion in its core pushing things outwards. But once a star dies, nuclear fusion stops. And so, like a bad day at Weight Watchers, gravity wins. When relatively small stars like our Sun die, they first expand into a red giant. Their outer gaseous envelope eventually detaches, floating away as a planetary nebula, and leaving behind a white-hot stellar core of oxygen and carbon supported by degenerate electron matter, known as a white dwarf, which will slowly cool over the eons of time. However, far more massive stars are destined to experience a very different fate. When they die, they collapse under their own immense gravitational forces, crushing their masses inwards before exploding as a core collapse supernova, an event bright enough to outshine an entire galaxy. What's left behind is a neutron star, a superdense object in which electrons and protons have been crushed together forming neutrons, and only supported from further collapse by neutron degeneracy. These objects are so dense that just a teaspoonful of neutron star matter would weigh more than 1 billion tons. That's more than a mountain range. And it doesn't end there. The collapse of even more massive stars at the end of their lives leads to even stranger, more dense objects, black holes. Both the author of this new study, Raul Cabello-Rubio from Italy's International School for Advanced Studies in Trieste, says science could be missing something, another type of stellar remnant born out of the death of a star. Cabello-Rubio says this hypothetical star would include the repulsive force of quantum vacuum polarization to describe ultra-compact configurations of stars which were previously thought impossible to exist in equilibrium. He says because of the attractive and repulsive forces at play, a massive star can either become a neutron star or turn into a black hole. In neutron stars, stellar equilibrium is the result of the fight between gravity, which is the attractive force, and a repulsive force of degeneracy pressure, preventing two or more identical fermions, that is mass particles, from occupying the same quantum state in a quantum system simultaneously, as per Wolfgang Pauli's 1924 exclusion principle. So, if the mass becomes greater than the Chandrasekhar limit of 1.44 times the mass of the Sun, then the stellar remnant will collapse beyond the electron degeneracy state of a white dwarf and become a neutron star. And if the mass becomes greater than 2.16 times the mass of the Sun, then the stellar remnant will continue to collapse beyond the neutron degeneracy state of a neutron star and become a black hole. However, Cabello-Rubio hypothesizes there's more at play here. That's because of those bubbles of quantum vacuum polarization we mentioned earlier. They too need to be included. Cabello-Rubio says the novelty of his idea is that all these ingredients have been assembled together in a fully consistent model for the first time, resulting in what he describes as semi-classical relativistic stars. Now, he admits it's still not known if they really could exist or for how long. But if they do exist, they should look very similar to stellar mass black holes. But of course without the black hole's event horizon, which provides a point of no return for energy, matter and time falling towards the black hole's singularity. The other important point here is that if they are like stellar mass black holes, that means we should be able to see them using new generations of gravitational wave observatories. And the idea of that is fascinating. I'm Stuart Gary. You're listening to SpaceTime. Scientists have released the latest data from NASA's Juno spacecraft's most recent encounters with the gas giant Jupiter. The probe's undertaking a series of highly elongated 53-day orbits around the solar system's largest planet. These eccentric orbits are designed to fly low to within 3,500 kilometers of the swirling Jovian cloud tops, and then swing out wide to avoid as much of the planet's intense radiation belts as possible. Juno's instruments probe deep beneath the obscuring cloud cover, studying Jupiter's weather patterns, cloud structure and composition, the giant planet's gravity and internal makeup, and its auroral activity and magnetosphere, in order to learn more about Jupiter's formation and consequently the evolution of the entire solar system. See, Jupiter is more massive than all the other planets, moons, asteroids, comets and other solar system objects combined, apart of course that is from the Sun. It generates more energy than it receives from the Sun, and were it more massive, Jupiter probably would have become a second solar system star. Data collected during these latest orbits indicate that the atmospheric winds of the gas giant run deep into the atmosphere, and they last far longer than similar atmospheric processes found on Earth. The findings will improve science's understanding of Jupiter's internal structure, its core mass, and eventually its origin. Other Juno science results show that the massive cyclones that surround Jupiter's north and south poles are enduring atmospheric features unlike anything encountered anywhere else in the solar system. The findings are among 4 papers reported in the journal Nature. Juno's principal investigator, Scott Bolton from the Southwest Research Institute in San Antonio, Texas, says these astonishing results are yet another example of Jupiter's many curveballs. In fact, Juno is only a third of the way through its primary mission, and scientists are seeing a completely different Jupiter to anything they had previously expected. For hundreds of years, since first observed through Galileo Galilei's telescope, the solar system's largest planet appeared shrouded in colourful bands of clouds extending from limb to limb. These salmon and cream-coloured zones and belts were thought to be an expression of Jovian weather, related to alternating winds blowing eastwards and westwards at different speeds. The depth to which the roots of Jupiter's famous zones and belts extended has long been a mystery. But now gravity measurements collected by Juno during its close flybys have finally provided an answer. Juno's observations show that these east-west flows, also known as jet streams, penetrate deep within the planet's atmosphere, down to depths of 3,000 kilometres. In fact, Juno's measurements of Jupiter's gravity indicates a north-south asymmetry similar to the asymmetry observed in its zones and belts. Now, on a gas planet, such an asymmetry can only come from flows deep within the planet, and on Jupiter, the visible eastward and westward jet streams are likewise asymmetrical north and south. You see, the deeper the jets, the more mass they contain, leading to a stronger signal expressed in the gravity field. So, the magnitude and the asymmetry in the gravity determines how deep the jet streams extend. As I mentioned, Galileo first viewed stripes on Jupiter's surface more than 400 years ago, but until now, scientists only have had a superficial understanding of them. And now, following these Juno gravity measurements, scientists know how deep the jets extend and what their structure is like beneath the visible cloud tops. It's like going from a two-dimensional picture to a 3D version in 4K high definition. Needless to say, the result was quite a surprise for the Juno science team, because it indicated that the weather layer of Jupiter was more massive, extending far deeper than previously expected. This 3,000 kilometre deep Jovian weather layer contains about 1% of Jupiter's total mass. Now, that might not sound like much, but that's actually equivalent to about 3 times the total mass of the planet Earth. And by contrast, Earth's atmosphere is less than 1/millionth the total mass of Earth. The fact that Jupiter has such a massive region rotating in separate east-west bands has come as a huge surprise. And the finding is important for understanding the nature and possible mechanisms driving these strong jet streams. In addition, the gravity signature of the jet streams is also entangled with the gravity signal of Jupiter's core. Amazingly, another Juno result suggests that beneath the weather layer, the entire planet is rotating nearly as a rigid body. Future measurements by Juno will help researchers understand how the transition works between the weather layer and the so-called rigid body below. Juno's new discovery also has implications for other worlds in our solar system and beyond. The results imply that the outer differentially rotating region should be at least 3 times deeper in Saturn, and shallower in many massive gas giant exoplanets and brown dwarfs. A truly striking result released in the Nature papers is the new imagery of Jupiter's poles captured by Juno's Jovian infrared auroral mapper instrument. And we've included heaps of these images on our SpaceTime blog. Just go to spacetimewithstuartgary.tumblr.com. The auroral mapper captures images of light emerging from deep inside Jupiter equally well night or day. It probes the weather layer down to about 70 kilometres below the Jovian cloud tops. Prior to Juno, scientists had no idea of what the weather was like near Jupiter's poles. But now they've been able to observe polar weather close up every 2 months, seeing multiple cyclonic vortexes thousands of kilometres wide, with violent winds reaching speeds of more than 350 kilometres an hour. But perhaps the most remarkable feature is that these multiple cyclones are all very close together and enduring. There's simply nothing else like them in the solar system. Jupiter's poles are in stark contrast to the more familiar orange and white belts and zones encircling the planet at lower latitudes. Its north pole is dominated by a central cyclone, surrounded by 8 circumpolar cyclones with diameters ranging from 4,000 to 4,600 kilometres wide. Jupiter's south pole also contains a central cyclone, and it's surrounded by 5 even larger cyclones with diameters ranging from 5,600 to 7,000 kilometers across. Almost all the polar cyclones of both poles are so densely packed that their spiral arms come in direct contact with adjacent cyclones. However, as tightly spaced as these cyclones are, they've remained distinct, with their individual morphologies remaining intact over the 7 months of observations undertaken by Juno so far. Of course, the big question is, why aren't they merging? As we know from Cassini's observations of Saturn, that ringed world has a single cyclonic vortex at each pole. In fact, the one at the North Pole often looks strangely hexagonal. What scientists are now beginning to realise is that not all planetary giants are created equal. The Juno spacecraft was launched on August 5, 2011 on an Atlas V rocket from the Cape Canaveral Air Force Base in Florida, achieving Jovian orbit insertion on July 4, 2016. The probe has now completed 10 science passes over Jupiter, logging more than 200 million kilometres since its arrival. Juno's next close encounter with the Jovian cloud tops will be on April the 1st. I'm Stuart Gary. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. A British inquiry says either the Russian government of Vladimir Putin was responsible for the attempted murder of former Russian double agent Sergei Skripal and his daughter, or Moscow has lost control of its nerve gas stockpiles. The unprecedented attack by British Prime Minister Theresa May also named the nerve agent used to try and kill Skripal and his daughter as Novichok, which was developed illegally by the Soviet Union and later Russia in the 1970s, 80s and 90s. Novichok's understood to be the deadliest nerve agent ever made, up to 8 times more potent than VX or sarin. Initially designated as K84 and later renamed A230, Novichok comes in over 100 variants, with A232 or Novichok 5 being considered the most promising. Novichok was specially designed by the Russians to circumvent United Nations chemical weapons convention lists. It was also designed to defeat NATO chemical weapons protective gear and be undetectable by standard NATO chemical weapons detection equipment. Although Russia initially denied any chemical weapons program, it was subsequently proven that Russia was in fact expanding its chemical weapons capabilities, using money it had received from the West for the disarmament of chemical, biological and nuclear weapons of mass destruction. Less potent versions of Novichok have been described by the Russians as organophosphate insecticides, so that Moscow's secret chemical weapons program could be disguised as legitimate pesticide research. Before being moved to Moscow following the fall of the Soviet Union, one of the key Novichok manufacturing sites was the State Scientific Research Institute for Organic Chemistry and Technology in Uzbekistan. The Uzbekistan government is now working with the United States to try and decontaminate the facility. Apart from its high lethality, what makes Novichok so useful is that it can be dispersed as an ultra-fine powder, as well as the more conventional liquid, aerosol and gas forms. In line with other nerve agents, Novichok works by targeting and inhibiting the enzyme acetylcholinesterase, preventing the normal breakdown of the neurotransmitter acetylcholine at nerve junctions or synapses. Acetylcholine has a vital role in the body's autonomous nervous system, which controls things like heart rate, respiratory activity, digestion, pupil dilation, and even urination. Without one of the major off switches of the body, all the lights are turned on all the time, and the body will very rapidly run into trouble. With an extremely rapid buildup of acetylcholine in synapses, things like secretions, respiratory problems, and muscular dysfunction can go unattenuated. Victims show convulsions, drooling, white eyes as pupils are constricted, and eventually they fall into coma. There's respiratory failure and cardiac arrest as the victim's heart and diaphragm muscles cease to function normally, with death usually resulting from either heart failure or suffocation as fluid secretions fill the victim's lungs. Doctors use atropine to try and block the receptors where the acetylcholine acts in order to prevent the nerve agent's poisoning. However, despite what you may have seen in the movies, atropine is really difficult to administer safely. That's because its effective dose for a nerve agent poisoning is very close to the dose at which patients can suffer potentially fatal side effects. The speed with which the nerve agent took hold of Skripal and his daughter meant scientists were able to quickly rule out radiation poisoning, which takes tens of hours to several days to show symptoms after exposure. At least 19 bystanders were also affected after accidentally coming into contact with the deadly nerve agent. Police are now also exhuming the graves of Skripal's deceased wife and son to see if they were also killed by Novichok or another nerve agent during what may have been a previously unrecognised earlier attack. Skripal was once a colonel in Russia's GRU military intelligence service. He was arrested in 2004 and imprisoned on charges of high treason after it was determined he was a double agent. He was among 4 Russians exchanged in 2010 in a spy swap deal for 10 deep-cover Russian sleeper agents that had been planted by Moscow in the United States. Prior to the identification of Novichok as the nerve agent, both VX and sarin had been suspected. VX, together with chlorine gas, are being used today by Vladimir Putin ally Bashar al-Assad against his own people in Syria. VX and chlorine gas were also extensively used by Bashar al-Assad ally and fellow Ba'ath Party member, the former Iraqi dictator Saddam Hussein. And VX has also been used by North Korean dictator Kim Jong-un, who supplied his agents with it to kill his brother at Kuala Lumpur airport in 2017. The other suspected nerve agent was sarin. It was used by the Shinrikyo Doomsday Cult in the 1995 attack on the Tokyo subway, which killed 13 people and injured 5,500 others. The Skripal case has strong parallels with the murder of ex-KGB agent Alexander Litvinenko, who was killed with radioactive polonium-210 in London in 2006. In a deathbed statement, Litvinenko said he was murdered on the direct orders of Russian President Vladimir Putin. Putin is a career KGB agent and became head of its replacement, the FSB, following the collapse of the Soviet Union. In 2016, a UK public inquiry found that 2 Russian secret police agents carried out the poisoning of Litvinenko, most likely on the orders of Vladimir Putin, through the FSB. In fact, it's worth noting that literally dozens of outspoken opponents of Vladimir Putin seem to have had curiously high exposure rates to some of the most exotic, lethal and toxic agents ever known. These days, ancestry DNA tests are all the rage, but scientists have found that environmental factors such as air pollution can have a bigger effect on gene expression than what you've inherited from your folks. A new Canadian study, reported in the journal Nature Communications, examined thousands of people in Quebec, where most people are descended from a group of French settlers. The authors found gene expression linked to cardiometabolic and respiratory traits were far more affected by air pollution than what they were by the group's ancestry. Another week and another study on the frequency of sexting among children. Sexting is the practice of electronically sharing sexually explicit material. This new study, reported in the Journal of the American Medical Association Pediatrics, found that 1 in 7 kids under the age of 18 have sent a sexting image to someone else, and 1 in 4 kids admit receiving them. The new study was designed to remove any lack of consensus on the frequency of sexting among kids. To achieve that, researchers involved some 110,380 kids between the years 1990 and 2016. Still on adolescence, and a new study claims teen gamers have just as many friends at school as their non-gamer peers. The findings by researchers at Uppsala University are based on a study of how digital gaming affects young people's friendship formation rates. The results show that neither the adolescents who spent much of their time gaming nor those who self-identify as gamers have fewer friends than their peers who play little or not at all. However, the study, based on an analysis of 115 Swedish upper secondary school students, found that most gamers' friends are other gamers. However, researchers say that's nothing to worry about, because just as adolescents used to get together through shared music tastes, so gaming nowadays is the key element in media consumption. Well, it seems old-school style cell phones are making a big comeback, with HMD announcing plans to introduce another new smartphone version of the classic Nokia mobile phone. Alex Zaharov-Reutt from IT Wire reports the new phone will be based on the styling of the old Nokia 8110 4G.
Original Nokia was different in that instead of just being a standard candy bar design, it not only had that shape, but it was curved. And then the actual buttons on the phone were covered by a slider that you could manually sort of slide out. Now, a lot of people might remember this phone as being the phone that Neo used in The Matrix. And in fact, in The Matrix, they actually retrofitted a spring so that it would, when you push the button, it would sort of snap out, and come out. That's not how it worked in real life, though. And for the new version of this phone, the 2018 version of this phone, they actually considered putting a slider in and wanted to put the spring in there so it would, snap out. But when they actually ended up doing it, the design was too thick and it just didn't look anywhere near as sleek or as good as having the slide that you slid out manually. So that design at the time was an iconic design. I remember having it. Really, it was no different from the other Nokia phones of the day, except for two things. One, it was curved, sort of like a banana or like a phone handset. And secondly, it had that slide. There were other phones that had slides. The StarTAC phones from Motorola had the flip. There were a lot of flip phones, and they're pulling the slide
I had a Motorola
down,
flip.
Flipping the phone up or down or sliding the phone up or down would answer or hang up the call, respectively. This phone has been brought back for 2018, and obviously it's been modernized. The slide itself, will answer and hang up calls, but you also have a number of other things on the phone, such as Google Assistant, Google Maps. You'll have apps for Facebook and Twitter. You'll have the ability to do your Outlook and Gmail, and there will be a small app store for it. But this phone is actually using something called Kai OS, and this is the Firefox Os Reborn. Firefox, the people who make the browser, actually made a phone OS, and they tried bringing it to market and making it successful, and it never really took off because it's hard to make it or break it against iOS and Android. But this phone has found new life as a feature phone OS, and interestingly, you've got in Asia, according to Strategy Analytics, one of the big analytics firms, 400 million feature phones were sold in Asia in 2017, and obviously most of Asia is in first world, and these feature phones are a lot cheaper than the traditional Android or iOS phones, and because they don't have to run the more complicated Android and iOS apps, they can get away with having a simpler operating system, less RAM, and in the case of the Nokia 8110, they're saying up to 25 hours of battery life. They do have caveats saying that's without any other apps running, but in theory, you'll get 2, 3, 4 days out of this phone like you would with the old-fashioned Nokias, depending on how much you're using it. And it's a retro blast from the past.
That report by Alex Zaharov-Reutt from IT Wire. You're listening to SpaceTime. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favourite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary. At SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.